All right, we're going to finish up sum and difference 5-4 day 1, part 2. Now, we didn't quite get to the verifying identities in that part 1 video, so we're going to finish up with verifying identities for this day 1, part 2. So how can I verify identities or prove that things are true? So we're going to pick up where we left off from part 1, and we're going to verify this cofunction identity. So remember we talked about cofunctions earlier this year, like sine and cosine are cofunctions. If we think about the graphs for sine and cosine, they're exactly 90 degrees or pi over 2 off. So we're going to talk about this one a couple different ways, but look at are these two things actually equal? And it's using a difference formula. So we're going to go back and just use what we know about the difference formula to actually prove this identity, to verify it, to show that it's true. So our u is like the x, and our v is the pi over 2. So I'm just going to write out the formula for the difference of two angles using x and pi over 2 as my u and my v. So the sine formula, so we'll go back to our formulas here. So I'm going to zip back up so we can look at those. So we're looking at the difference of 2. So we're looking at this one where the u is the x and the v is the pi over 2. So we're just going to replace that and see what we come up with. So it's sine of the first angle, x, times cosine of the second angle, pi over 2. Now, if that's a subtraction, in the formula it's a minus, so we have to follow whatever the signs are. So the x and the v, or the x and the pi over 2, or the u and the v, the sign is whatever it needs to be in that relationship. So just follow the sign as it is in the formula. So sine, cosine, and then we have cosine of the first angle, and then sine of the second angle. You'll hear me say first and second a lot. It's the same as u and v. Sometimes it's easier for people to think in those terms, just like the first angle and the second angle in the difference. We're supposed to be showing that it's equal to negative cosine of x. So anything that has a special value, we can evaluate. So I'm going to actually put in the values for those. So that would be sine of x times, okay, what's the cosine of pi over 2 or 90? Well, that's 0. And then we're going to do the same thing over here. What's the sine of pi over 2? Well, that's 1. And we'll see what we have left. Now, these verify are going to be a whole lot easier than some of the verify that we were dealing with earlier, because with these special values, things get pretty easy. 0 times anything is just 0. 1 times anything is just the anything. So negative cosine of x is equal to negative cosine of x, and we verified that identity. A really cool way to look at this one is to also verify it graphically. So this was an algebraic approach, what we just did. Let's take a look at the graph. So I'm going to have you go ahead in your graphing calculator, double check your mode. We're going to go back to radians. I'm going to have you put the left-hand side in your graphing calculator in your y1. So sine of x minus, and then we'll do, oops, sorry, I'm trying to get my pi over 2 in here. So pi over 2. So I'm going to have that be my my y1, and in y2 I'm going to do negative cosine of x. So I'm going to put in those two equations, and what I want to see is what happens if I graph them. So if these are actually equivalent, that means their values should be the same. So what should be true about the graph? They should be identical. So I'm going to just do a zoom 6. I have no idea what my window is right now, so just a standard window. There's the first one, there's the second one. Awesome way to show that, oh, yep, these are exactly the same equation. They have the same outputs. That's how we know that when we verified them, that they're going to give us the same value. So it's kind of a cool way to look at it. So remember, we have different ways to approach solving problems numerically, graphically, algebraically. They can all show us the same thing. All right, so we're going to talk about kind of going the opposite direction then of these verify. It's using something called a reduction formula, kind of a neat way to think about going backwards in one of these scenarios. So a reduction formula is just a formula that expresses a trig function of any angle in terms of an acute angle theta. So being able to take something that we have, like whatever trig function is of any angle, using a quadrant 1 angle. So they're talking about when you reduce something, you make it smaller. So basically expressing any other angle using only like a quadrant 1 angle, something that's easier, that we're more familiar with. So thinking of a harder, larger angle and expressing it in terms of a smaller or easier angle is kind of a good way to think about that. So let's talk about what that means for something like this. So the angle that you have is t plus pi over 2, which is an angle bigger than pi over 2 because we're adding to it, right? Reduction formula just means use your sum and difference formula that we know, and write out what that means and put in any values that you have and see what it would be equivalent to. So it's really just evaluating and using your sum or difference formula. But what you're going to find is instead of having this more complicated angle, you're going to have it in terms of just a single angle, acute angle in quadrant one. So let's see what I mean by that. So in this case, if it's a sum, the u is like your t, the v is like your pi over 2. We're literally going to write out the sum formula again for the sum of two angles. So sine of the first angle times cosine of the second angle. And if it's a sum in the sine formula, that means it's still going to be sum. And then it would be cosine of the first angle t times sine of the second angle pi over 2. So really, it's a lot like what we just did for verifying an identity. We just didn't have the other side of the equation. We're kind of coming up with what that identity is. How can we write this in an easier way? Anything, again, that has a special value in it, you can evaluate. This is going to look a lot like what we just did. So sine of t times what's the cosine of pi over 2? Well, 0. And then cosine of t times what's the sine of pi over 2? 1. Anything times 0, obviously that's 0. So we're left with just cosine of t. So this sine of t plus pi over 2, a more complicated angle, we just derived one of the cofunction formulas, is actually equal to the cosine of t. So the reduction formula, the idea is I just wrote this in an easier way. Just one single angle, just this t. And again, if we wanted to check it and see if this is true, we could go back, and I'm just going to make a little adjustment here. This is the sum of the two, so I'm going to make that a plus. And instead of having a negative out front, I'm going to ditch that. And look what happens. Same thing as the last one. So a reduction formula just means, hey, is there an easier way that I can write this? And using sum and difference formulas to find those is really handy. So if you express it, write it out, we can maybe make that a little bit easier. So we're going to do this for the next one. We're going to do the same thing. So we're going to do a difference formula and see if we can come up with an easier way to express that, knowing that I can use my sum and difference formulas to do this. So my u is like the theta and the v is like the pi over 4. And it's a difference formula. So for tangent, it's tangent of the first angle minus tangent of the second angle, pi over 4, over 1 plus tangent of the first angle times tangent of the second angle. So what our goal here is to try to get rid of as many terms as we can by evaluating, knowing those special values and seeing if we can come up with an easier way to express this. All right, so tangent of pi over 4 is something that I know, 45 degrees. So that would be tangent of theta minus 1 over 1 plus tangent of theta times 1. Well, tangent of theta times 1 is just tangent of theta. So we'd have tangent of theta minus 1 over 1 plus tangent of theta. So you could also say tangent of theta plus 1 there on the bottom if that was a more comfy way for you to be able to say it. So it actually turns out pretty well that we can come up with an easier formula. And notice it only uses tangent of theta. We get that single angle measurement that's a little bit easier. So a lot of times people will use sum and difference formulas as what they call a reduction formula, or a way to express something in a little bit easier way. So that was kind of the last piece for this part one, to be able to either verify or use sum and difference to help write a simpler equation.